Hey, hello there. Let's talk about today's Leetcoding challenge question, add digits. Given a non-negative integer, we want to repeatedly add all its digits up until the resulting number has only one digit. Looking at the example, we have the integer that's 38. So we add all its digits up. 3 plus 8, we get 11. The output number is still not a single digit number, so we have to repeat this process again. We add 1 and 1, we get 2. So the output is now a single digit number. So the process terminated, and we return that as the output. So that's the question and the example and how the process looks like. The brute force solution is basically to simulate this process. Until the number has been transformed into a single digit number, we have to repeat this replace the number by its sum of its digits. So let's just code that out. Let's just change the input to x so that in further analysis the notation become a little bit simpler. Until that this number has been less than 10, meaning it's a single digits, we can forget about this transformation. Otherwise, we have to repeatedly transform the number by its sum of its digits. So the function transformation function is to replace x by the sum of its digits. So we do a div mod with the input number x by 10 to truncate its last digits and also extract that last digit, add that to the accumulation s. So in the end we just return s. So this process is basically simulating the question requirements, and this solution should work. So that's the brute force simulation process. Let's talk about the issues here. We need to somehow show that this while loop wouldn't be running indefinitely, so it will converge somehow. Let's show that. So the first question is, will this converge? This process converge? So we're starting with the input x. If it's not satisfied our criterion, we're gonna replace it by fx, just summing up all the digits from x to transform that into fx. That's the second element in the sequence. And then if it's still not the single digit number, we have to apply that function again. So it's a higher and higher order function calls on the original input. We're basically interested in whether this sequence would converge. So to analyze that, we have to plug in the formulation for x and fx. X is basically adding up the digits multiplied by the correct power of tens. For last digits, you multiply by 1. For the second tens position digits, you multiply that digit by 10 and add all those up. That's what this summation here is. The fx is to adding just the digits without the multiplication of the power of tens. So the only difference between fx and x is that in the summation part, x has the power of 10. The fx does not have that. So it's very clear that when we apply this function f on the input x, the resulting has to be less than or equal to x. So that just shows that this sequence is decreasing until it converges. Once it converges, it's repeating itself because we're looking at a single digit number. So fx and x will become the same number. So that just shows that if we simulate this process, the while loop will definitely break in some point. So the second question now is, how fast would this sequence converge? Because that's the runtime complexity for this problem. So if we look at the formula for x, let's say that it has n different digits. So that in the formula we looking at we're starting with index 0, so the power works nicely. We know that the number of digits inside this number is roughly log 10, base 10 of that number. It should be ceiling in most of the situation, except for the case like full power of 10, like 10. Number 10 is actually 2 digits. But if you take log 10 of 10, it's just 1. So in that case you have to add 1. Otherwise, if like 20 or something, that should be 1 point something. If you take the ceiling, it will become 2. That tells you the number of digits in there. So that's what this n roughly is the total number of digits. If we plug that, if we look at the formula for fx, summing up all the digits, since that every digit has to be less than 10, otherwise it wouldn't be a single digit. So this summation is actually upper bounded by just replace every digit with 10. So it's 10 multiplied by n. So adding the information about the number of digits, we can see that the series is basically having the original input, transform that into something that's less than 10 multiplied by log 10 of x. And the next element in the sequence is log 10, base 10 of that second element in there. So it's repeatedly taking log 10. So the runtime complexity will be order of log base 10 of x. Now, so that shows how fast would this converge. So this code here, simulate will be in log time. So let's talk about the follow-ups. Could we solve it without any loop or recursion in constant time? So this is clear that we have to look for some kind of pattern for this problem. So for that reason, we're just gonna run this simulation process on a bunch of numbers in sequence and see can we find any kind of pattern in there. Maybe run this up to 100. Yeah, so let's see how it works. Just run this on a bunch of number in sequence and see is there any kind of pattern in the output so that we can derive some kind of formula. Because constant time is definitely a formula. It's not a code. So let's add self here. So this is the number by running this simulation, add digits simulation on numbers from 0 to 99. So 0 be transformed into 0, 1 to 1, 2 to 2. So below 10, for single digit number, it's just the number itself. From 10, it go back to 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 9, and 19 you become 1 again. And just if you keep looking and keep looking, it's repeating itself 1, 2, 3, 4, 5, 6, 7, 8, 9 over and over and over and over again. So it's clear that the pattern here is just do a modular of 9 and we can directly figure out the number. So the only special case is that when the input is 0, we output 0. Otherwise, we just have the number modular 9, and if the number is actually 9, the modular will become 0, but in this case we want to output 9. Otherwise, we're just directly outputting the number. So it's modular 9 or 9 itself. If it's 0, then we output in 9. So that's the formulaic solution to this problem. Now, so we derived this formula by looking at the output and find the pattern. Maybe the next step is to prove this is right. So let's talk about that. I don't have the text document provided, so you're gonna bear with me for my slow typing, especially the formula. So if you look at the formula here, it's basically without doing any of that simulation transformation, but directly modular the number by 9 and find out the number. Why is that the case? For single digit case, we start with the simpler case, right? Base case. So for single digit number, if you modular that by 9, you will get that number itself, especially if, except for 10, right? Except for number 9. Number 9, you modular 9, you get 0. So that's this. For a number that's less than 9, if you modular that by 9, you get that number back. Then that's the base case. So when the series converges, in the converge phase, the x is basically modular by 9. We can return that. Otherwise, we want to look at the relationship between x modular 9 and fx modular by 9. If they are equivalent, then that's saying we don't need to go through this process. We can just directly do modular on the x. So let's actually move this up so that you can see my changes. We want to show that x modular 9 is equivalent to fx of modular 9. If that's the case, then we can skip us through all this higher order function calls, directly apply this modular by 9, so that we basically know the single digit cases. So let's plug in the formula for x and fx onto that formula that we want to show that's equivalent. So to show that fx modular 9 is equal to fx modular 9, we plug in the formula. It's the sum of stuff modular 9 equal to sum of single digits modular 9. Let's put the parenthesis there so that you know the order of calculation. We do the sum first, then do the modular. Since it's sum of numbers, then modular 9, it's equal to the individual number modular 9, sum all those up, and then do a final modular 9. So that's to put the number to the modular inside here as well. And now let's look at the difference between those two. The difference is that the first term has, in the summation, it's di multiplied by 10 to some power of i's. This is equal to d multiplied by the single digit multiplied by 99999, a bunch of 9 plus 1. So that if you think about the modular, adding the modular into the consideration, and then you're just separating the summation from the second term there. It becomes d times some multiple of 9 actually. Let's actually just putting that onto the second line here because it's a little bit crowded. Now the first term here, d multiplied by 9999999 modulo 9 is 0 because 9999 modulo 9 is 0. So the first term is effectively 0. So that reduced the whole thing into the second term there, d modulo 9. So now we're basically just showing that these are indeed the same because 10 to the power of I, di multiplied by 10 to the power of I modulo 9 is equivalent to this, the second term on the right hand side. So we showed that x modulo 9 is equal to fx modulo 9, and it's going to be equal to f of fx modulo 9 all the way go back to a single digit case. And so that's showing why this formula works. Yeah, so after kind of show why this formula works, we can say that now we can justify why this works. The time complexity is definitely constant. Alright, so that's the question today, and it's not a proof, it's just a sketchy sketch kind of showing that why this is working. It's not a proof. Alright, so that's the question today. It's more of a math problem rather than a programming problem.